So today is lecture 12 about invariant maximality reversal by Harvey Friedman, please.
Yes, thank you. So I finished the proof. We finished the proof of the reversal. Um, the formal definition of the crucial invariant graph G, we're not going to lecture on. You will see it. It's a section 6 now. It's just the official definition of the whole thing. Um, and the plan is that the entire reversal manuscript will be shortly placed on my downloadable manuscripts page. And then this lecture, as usual, will be in the downloadable manuscripts page. Sorry, the downloadable manuscripts page will be the official whole chapter 4 reversal, and then this will be added. This lecture here will be added. The text of this will be added to the downloadable lecture notes page. All right. So today is a discussion of the base theory for the reversal, which takes some discussion, and also the result that ZFC, and in fact, any fragment of SRP, isn't enough to prove every instance of the reversal statement on dimension. In other words, you get a hierarchy as the dimension goes up. So we need to actually establish that. Yeah. Okay. So lecture 11, you can get on the lecture notes page, and it was on 4.1 and 4.2 of the reversal, and that's already also on the manuscript page right now. All right. So we are reversing this as usual, and we have this table of contents. And so we've gone through lectures specifically on every one of these things except 6. But you'll see that in the final version of the chapter 4. I mean, we use pieces of this as we use the graph all through the reversal. Actually, the graph only got used. The graph only really got used in here. Remember, we graduated away from the graph and the invariant maximal clique. We graduated away from that. So in this section, that was also assumed in M, and this section didn't refer to the graph anymore or the invariant maximal clique. All right. So we want to talk about the base theory that we use for this reversal. Basically, the reversal is almost entirely done without much modification, maybe a little bit of modification in the system ACA prime. And this system is stronger than ACA naught, stronger than arithmetic progression, stronger than ACA naught. This is a finely axiomatized system, well-known system, extending ACA naught with the axiom for every x and integer n, the nth Turing jump of x exists. Yeah. All right. Now, we make some substantial changes, putting the reversal in WKL naught after we make very few changes to do it in ACA prime. And to push it down to WKL naught takes some discussion. It's not too bad. And then we argue mathematically that WKL naught can be replaced by RCA naught. And this can be done without going back into any reversal because of a metamathematical fact that any statement of a certain form that's provable in WKL naught is already provable in RCA naught. So we'll do that. So then we have this, that our statement implies con SRP. Now we also worry about this. Oh, and this is my new notation. If you take our statement that we're reversing and you fix a dimension k, then we write colon k, not the semicolon, has to do with what this function is, what this function is. So the colon k means that I fixed k as the dimension. And this is the result, yeah, and treating k as a constant. Okay, so we also do this for SRP. I think I've discussed this before. SRP has a hierarchy, well-known hierarchy, because SRP itself is just a scheme, is just a scheme on K. And we show that for every K, there's an N such that SRP-N does not prove, I think I have this backwards. For every N, there exists K. Yeah, I always keep the K in the statement. For every N, there is a K such that SRP-N does not prove the statement with K fixed. Assuming, of course, that SRP-N is consistent. Yes. It's a little tricky to actually do this without more assumptions. It's easier to do this if you just assume SRP as a whole is consistent. But this is better. For each N, there is a K like this, just assuming SRP of N is consistent. In particular, ZFC does not prove this statement every instance, assuming ZFC is consistent. This is the main thing that that a mathematician, non-specialist, would like to know. That not only is this statement not provable in ZFC, you can't even prove any instance. Now, I have to say that the reversal that I give says absolutely nothing about a counterexample here. It says absolutely nothing about how high a dimension I have to go in order for ZFC not to prove. Nothing. And that's a big deal question. Uh, when we talk about the positive results, we see that it's highly suggestive that ZFC does not prove this for k equals 3. We do actually prove it in a little bit more than in a fragment of Z3, third order arithmetic, when k equals 2. But that's not for today. That's positive results. Okay, now this new material appears in section 411, and I think that the 411 section that's on the web page now was cut off before this material because I didn't talk about it at the time here. But it actually appears in the manuscript, chapter 4, after we finish the reversal. I then take up the issues that we're talking about today, connected with the base theory. All right. So we begin with a review of the logical structure of the reversal without let me say without substantial refinements. Yeah. Then we probe deeper and show that WKL naught is enough as a base theory. Finally, we argue formally to establish that RCA naught is sufficient. Okay, I said that before. All right, if you remember, the reversal began by fixing k to be any integer that's big. 2 to the 2 to the 2 to the 1,000, that's a pretty big number. Let's say, let's do this. Yeah. Well, it's really in the statement. So let me, yeah, I called it proposition A when I did this. But this is actually in the statement we're reversing, just to be pedantic about this. We then defined a particular order invariant graph. Um, on here. Yeah, maybe I should say it this way. I mean, I'm just trying to be accurate about what I'm talking about. I don't know. So a matter of English here. Okay, we then define an order invariant graph on here, and we let S be any maximal clique in G, which is also invariant. And G is very effectively obtained for K, so its full definition was postponed to section 4.6. So in section 4.1 and 4.2 that we did last time, we do basic preparatory observations about GNS. So far, we stayed obviously within RCA naught, except for the semantics. We gave the semantics for the full language in section 4.1, which gets used only, that language, L of K, gets used only much later in section 4.7. In section 4.3, we started working with the structure with the structure where we have the domain Q minus 1, 1, and we have the invariant clique, the maximal invariant clique S, which is K12 dimensional with order. In particular, with satisfaction for certain explicitly finite fragments of the associated first order language. You remember those three finite fragments, finite languages. Um, If we use the full language, we would be using more than ACA naught, but ACA would be comfortably sufficient. But since we're only using finite language fragments, ACA naught suffices here because we only have satisfaction for finite complexity. Technically speaking, since K is a definite number, the way we did set this up, we can get away with ACA naught because it's a standard integer, but we'll ultimately be generalizing over K in section 4.10. And so we are really using ACA naught prime thus far. In other words, we're going to reflect on the fact that K was arbitrarily picked, even though it was a particular number the way we developed the reversal. That was just a way of making everything more comprehensible. All right, in section 4.4, we work with the notion of good element of Q minus 1, 1. If you remember, that was a number less than or equal to 0 for which you could shift one place between statements with parameters below the place you're shifting, below the good element. And so that's a universally quantified statement being good. So in the presence of ACA prime, the set of good rationals exist, and even with K indefinite. So you really need ACA naught for that. And we then show that there are arbitrarily large good negative rationals, if you recall. Uh, and by RCA naught, we have the function that returns a negative good rational greater than any given rational. A negative good rational greater than any given rational. If K is fixed but indefinite, we can do that. And then we perform a primitive recursion in order to get this converging to 0. That's just a primitive recursion. Since we can talk about goodness. And in this way, we could clearly continue to stay within ACA prime throughout section 4.4, even interpreting this fixed number K as an indefinite number, without it being standard. Section 4.5 continues to stay within ACA prime with no issues, culminating with the structure, this structure here. All right, in section 4.6, that's just an explicit bookkeeping section where the ordered variant graph G is fully defined. So that's really basically a combinatorial section. Section 4.7 starts with this structure, and the only remnant of section 4.1 through 4.6 that remains. So, we're out of talking about G or S, out of talking about the graph G or the um, arbitrarily chosen invariant maximal clique. Now, here we upgrade M representation for the finite language, this finite language, to M representation for the infinite language. This is what's done, and the main point in section 4.7. Now, we don't have to define satisfaction for the full L of K language directly as a set, but instead have the satisfaction relation for the fragments of L of K with only finitely many quantifiers. In other words, we just need partial satisfaction sets. And that way we stay within ACA naught. Partial satisfaction relations is good enough. All right, in section 4.8, we continue to work within M, and we develop crucial properties of the internally well-founded prelinear orderings. We just need satisfaction for fragments of L of K again, and so we comfortably continue to stay within ACA prime. In section 4.9, we pass from M to our first internally well-founded linearly ordered structure, W. All right, now this is a weak second order structure in the sense that the sort set is a family of subsets of D, and U1, U2 are unary predicates on set. D is a set of equivalence classes of elements of Q0 infinity under a bounded M defined partial equivalence relation on Q0 infinity. Using this internally defined isomorphism relation between uh, internally internally pre-well ordered systems. So, as is standard, we stay within ACA prime by using the partial equivalence relation and avoid taking actual equivalence classes. This is a move that's used a lot in logic to avoid going to a higher type by by not taking the equivalence classes, even though conceptually it'd be nicer to do so. In this way, the structure W is interpreted in M via, so this W is interpreted in this old M here, this W and this M, via bounded formulas in L of K. So again, we stay within ACA prime. Section 4.10 is already set up. It was convenient to already set it up to support the weaker base theory WKL naught instead of ACA naught prime by moving from particular structures where these indiscernibles are unbounded to structures where they're possibly bounded as models of effectively given first order theories. But we can continue our account here using ACA prime since we've already been using AC prime. We don't really gain anything for the purposes of this preliminary discussion with ACA prime because we already committed to more than a WKL naught. But this tail end of stuff in 410 is WKL naught like because we're talking about theories, first order theories, uh, and the structures are just models of them. We need to show that the axioms T sub k in theorem 410.1 are formally consistent in order for us to build a model within WKL naught. We have the model x equals W, and so we only get the formal consistency using the full satisfaction predicate for W, which is not available in ACA prime. In other words, this problem of satisfiability implying consistency is always a problem. But you can use cut elimination to get away from the appropriate partial satisfaction predicates, to be able to use just the partial satisfaction predicates for W in order to get the consistency. So here we're generalizing over K so that the theory T used in theorem 410-2 is formally consistent and thus releasing the quantified K. So by completeness, T has a model X. This is this model X in the text with a satisfaction relation using only WKL naught here. And so we've stayed within ACA prime this way. Note that C1, C2 dot 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 may be bounded. That's the usual cost when you go to first order axiomatizations, because you can't say that it's unbounded this way. You know, it's not first order to say that. The crucial point here is that now both limited separation and indiscernibles use unlimited complexity. In other words, we really have L of K. Now, since we have X along the structure X along with a satisfaction relation, there's no problem completing sections 410 and 411 within RCA naught. Because we have the satisfaction relation, there's no issue anymore. In this way, we see that the base theory ACA prime is sufficient for yeah, maybe I need to say that this is for the statement. I want a statement we're reversing, where essentially the only modification needed is to use the form of completeness with satisfaction predicate available even in WKL naught in section 410, as we discussed. So with that modification at the end of this, we see that ACA naught is enough for the reversal. Here's the reversal statement, of course. That's the reversal. All right. We now have to indicate how ACA prime can be improved, not only to ACA naught, but actually down to WKL naught. The key idea is to use completeness with satisfaction predicate from the beginning, not just at a later stage, not just at a late stage. We go back to the starting structure, Q minus 1, 1 less than S, where S is the invariant maximal clique in the order invariant graph G. We fix the dimension, our length K for proposition A. Yeah, that's what I call A. There's the obvious A star, E star sentence phi. Well, let's just say it this way. There's the obvious A star, E star sentence phi in the language less than S, constants C naught through CK for the indiscernibles and another constant C. This C is for the left endpoint, and this CK is for the right endpoint, the last indiscernible. Namely, what is the appropriate theory here? It's that less than is a dense linear ordering with endpoints C and CK. These are strictly increasing. S is a maximal clique in G, and S is, this is an old remnant, is invariant. Yeah, sorry. This, yeah, right? Now we instead use the obvious A star sentence. This just means a block of universal quantifiers. And this means a block of universal quantifiers followed by a block of existential quantifiers. Yeah. And we just use witness functions. In other words, we add function symbols to produce the existential quantifiers. So that's what we want to do. We want to have this theory where it's universalized. And we see the structure Q minus 1, 1 less than S uh, given by, all right, can be expanded to a structure satisfying psi just using RCA naught. However, this does not automatically imply that psi is formally consistent. This problem about satisfiability implying consistency says that would involve inductions not available in WKL naught. However, we can use Herbrand's theorem because this theory is universal. Herbrand's theorem, which is available in WKL naught, so that we only need to interpret terms to obtain the formal consistency of psi in WKL naught from proposition A. Well, we use this thing instead. Yeah, I think this, I'm not sure I want to use proposition A anymore because it has a K-12 in it. I don't know. Anyways, this is just expositional. Interpreting these terms only involves relative primitive recursion, right? Because to interpret a term just because a term has only finite complexity, right? So, so we now use WKL naught to obtain a model of psi with satisfaction relation because we now know it's formally consistent. This will give us our structure where S is an invariant maximal clique in G with a satisfaction relation. So before, we just had this structure and uh, yeah, we just had this structure and we didn't we had trouble when we made first order uh, when we manipulated this with definable sets, we ran into some trouble. We needed ACA prime, but now we're getting around this. You see, we just use WKL naught for the full satisfaction relation. In section 3, we start working on the structure. The issues that pushed us into ACA naught before are entirely resolved since we have the satisfaction relation. That's the trick. In other words, do that up front. In section 4, the set of good rationals exists, K indefinite, from the satisfaction relation. Otherwise, it's universal quantified and it needs a jump, you see. And then the recursion uh, is available in RCA naught. It's just a primitive recursion, a relative primitive recursion. Now, there's no issues arising in section 4.4 to 4.9. We've already indicated how we complete sections 410 and 411 staying within WKL naught. Thus, we prove the following. In WKL naught. The statement to be reversed implies that there exists a countable model of SRP with its SAT and also just con SRP. We now show how to improve WKL naught with RCA naught for proving proposition A implies con SRP so that we can actually we improve this further down. So this requires a conservation result uh, that's credited to Leo Harrington with a full proof in Simpson's book. If you have a countable model of RCA naught, you can always extend it to a countable model of WKL naught with the same arithmetic part. Every countable model of RCA naught can be extended to a countable model of WKL naught with the same arithmetic part. RCA, and this, by the way, applies to non-standard models. RCA naught and WKL naught prove the same sentences of the form there is an N B, where B is pi 1, 1. That's a consequence. So for a reference to the first claim, Simpson's book, the first order part of WKL naught, there's a section called that. And this credited to Harrington in 1977 for the second. I think it's what's called Jacques-Soar forcing, where you force with finitely branching trees or something, if I remember right. For the second claim, suppose WKL naught proves there is an NBN, B of n. We now want to prove that RCA naught does. Suppose RCA naught does not prove there is an NBN. Let n be a model of RCA naught plus that's false for every n, not Bn. Remember, B is pi 1, 1. Let M star be given by the first claim, then M star satisfies for every M and not Bn. And this is a contradiction because M star satisfies WKL naught. Okay. See, the statement for every n not Bm is going to be preserved because we have the same arithmetic part and it's an expansion. We have more sets. So the ones in here are still around. Okay. So now we have to check only that we can actually use this, So we have to check that the statement we're reversing is of the right form. So this is just a calculation. So the statement we're reversing has the form for every n C of n, where the n is over the dimension, Well, it's more than the dimension, right? It's over the order invariant graph. It says every order invariant graph in every dimension, appropriate order invariant graph has a maximal clique. So the existence of a maximal clique, invariant maximal clique, sorry, that is sigma 1, 1, right? So it's for every n C of n, where C is sigma 1, 1. And we know that WKL naught proves, by the reversal, we know that WKL naught proves that our statement implies con SRP, right? So what does this implication look like? It's for every n C of n implies con SRP, right? And that's the same as there is an n not Cn or con SRP by logic. And that's the same as there is an n not Cn or con SRP by logic. And now we have to see what this statement is, not Cn or con SRP. That looks like, now remember, C is sigma 1, 1. So this is going to be pi 1, 1 or con SRP. And that's the same as you can put the disjunction in here for every E. Okay, where psi is arithmetic. So 6 is pi 1, 1. This down here is pi 1, 1, and 3 is of the form there is an n pi 1, 1. So 3 is of the form to which we can apply 4, 11, 23, this Harrington thing. And so by lemma 4, 11, 23, RCA naught proves 3, and therefore RCA naught proves 1. And that's just the statement we're reversing. Okay. So now we know that RCA naught is enough. Yeah, so we now have proved that RCA naught implies, this statement implies con SRP. The model theoretic form that this statement implies, there's a model of SRP. I guess is not claimed, but I don't need to claim everything. I can let you all improve my manuscript. So I guess maybe there's some possible improvement here, but this is the main point. Okay. Now, um, the last topic I promised is we look at we look at this statement. Sorry. Yeah. All right. Expositional. We look at this statement for the various K. Yeah. Okay. We can treat this with minimal adaptation of the reversal. I'd like to not go much into the reversal. I have to go into the reversal a little bit. I do have to, but I want to minimize that. Uh, okay, so maybe I haven't defined this yet. Yeah, I can't remember exactly how I'm going to set this up. Maybe I haven't defined this yet. That's just the colon means for fixed K. By the way, I once tried to do this. This is very bad because that K might be part of these list of numbers, right? And you don't want to do this. You don't want to do this. The semicolon is precious over there. So I pick a colon here. This is the best way to do it. This just means uh, we're fixing the K. All right. SRP of K is defined to be ZFC plus there is a lambda since the lambda has the K SRP. All right. Now I'm going to refer to stuff in the reversal, uh, but I don't want to really go writing these big long things in there. You can look them up. But they were these theories that these theories that were associated with these structures X, W, and a second form of W uh, in section 10. Um, so T of X is the theory we use to define X. X was a structure satisfying T. W is a structure satisfying T, and the second version of W is a structure satisfying T star. You probably don't remember the lecture on section 10 that well, but and 11, by the way. All right, so let me just briefly go through what goes on here. Um, the key fact that we want to use from the reversal that we'd already discussed is this. SRPN is interpretable in S star, T star W. And T star W is interpretable in T of W. So this is the back end, the last thing in the reversal. When we pulled out models of the SRPs by doing some large cardinal combinatorics in the non-well-founded structure at the end. And T star W is interpretable in TW. We're going backwards. And TW is interpretable in TX. And every finite fragment of TX is interpretable in some uh, in some fixed dimension. Okay, and this this is just from the way I set all that up in the reversal. All right, now there's a now we're ready to prove the theorem we want to prove that every SRPN is interpretable. Well, this is not quite what we want to prove, but this is the next step. Every fragment of SRP is interpretable in this statement with some fixed dimension. every SRP and is interpretable uh, in some version. So every fragment of SRP is interpretable in this statement we're reversing for some fixed dimension. And this follows from this technical thing here. This follows from this chain of interpretations. By the way, I should say, maybe I need to say, I have to do a little bit more work on the exposition here. We also, it's from the full reversal, we basically also showed that WKL naught plus the statement we reversed interprets the whole of SRP. Not only does it prove SRP is consistent, but it also interprets it. I mean, that actually more or less follows from it, but I think maybe I should have actually also said it interprets it. But this is just a dimension form of it. All right. Now we need a lemma that actually, I guess this is implicit in the literature, but it has a very simple proof. First of all, one form of Gödel's second incompleteness theorem is if T is a finely axiomatized system that proves EFA plus con T, then it must be inconsistent. But technically speaking, given what we're doing, we want to stick with interpretations rather than provability. So we actually need this. Let T be a finely axiomatized system that interprets EFA plus con T, then T is inconsistent. Yeah, I'm not sure that that's normally stated, but I'm sure that this is known to people. So the first one is just the usual. The second one, um, uh, so assume that T is that T interprets EFA plus con T, uh, that we can interpret it in T, then EFA plus con T proves con of EFA plus con T because arguing in EFA, any inconsistency in EFA plus con T gets converted by the interpretation to an inconsistency in T. So therefore, EFA plus con T is inconsistent by Gödel's second theorem. Hence, EFA plus con T is interpretable in T. Since EFA plus con T is interpretable in T, we have the T must be inconsistent. So this clears the air from not needing uh, that a base theory is in the system. You can just say it interprets it. All right. Uh, okay, so the above simple proof allows us to avoid assuming that T actually extends EFA, which is nice to have. All right, so then the final thing, and this is the final couple of things, a little technical, but you string everything together. Let T be a finite fragment of SRP consistent with WKL naught as naturally formalized in set theory. Because I want to use set theory here, I want to talk about WKL naught as naturally formalized in set theory. There exists K such that T does not prove our statement in dimension K. And you could get this from stringing things together. Although if I just go through this, it'll just sound confusing. And then you can do the same thing, the same idea using ZFC instead of a finite fragment of SRP. ZFC is not actually a finite fragment of SRP, but uh, you get around this because we just have to worry about finite fragments of ZFC. So we have finally here that if ZFC is consistent, it doesn't prove the statement we're reversing in every dimension. And that's, of course, something we want to highlight for non-experts, to say this. Now, what K do I need in order for ZFC to not prove this? And there's nothing here that even remotely suggests what K would be. And I didn't try to do this, or I know that it's some serious work. So, but I'm leaving that wide open. Now, when we do the positive part, that's chapter 3, uh, with the proofs, uh, we'll see that for K equals 2, that this is provable in Z3. But when K is 3, my proof goes way beyond ZFC. It uses a subtle cardinal. So that suggests, but doesn't establish by any means, that K equals 3 is the place where this starts. But this is, you know, a major issue. All right, Andreas, I think I'm done.